welcome to Max Meetup, this edition of Max Meetup by Music Hackspace. Today I'm your host, Umut Eldem. I am a doctoral researcher at the Royal Conservatory of Antwerp. I'm a composer, an audiovisual artist, and a musician in general. I teach Max MSP at the Royal Conservatory of Antwerp, and I do tutorial videos on my YouTube channel here in class. But enough about me, because today we have three fantastic presentations by three fantastic artists, and they're all going to present their own artworks and their approaches to incorporating Max MSP into what they're doing in the frame of generative art. So using external data, using live input from the audience, really generating the data in real time by using algorithms, random chance, you name it. So the presentations are going to be 15 to 20 minutes long. If we have time, we might have one or maybe two questions at the end. But after the presentations, for those of you watching it live right now in the Zoom meeting, we will have breakout rooms where you can further talk with each of the presenters. Maybe you want them to explain further their Max patches or their approach, or you just want to chat with them because they seem like really nice people. But in any case, so we are going to start with Can. Can Memişoğulları is a multidisciplinary artist from Istanbul, Turkey. His artistic practices include electroacoustic works, acoustic composition, new media art installations, AV live performances. He's also interested in human interaction and its consequences in art. And to examine this, he likes to create structures and systems that can decide and upgrade themselves with the help of their audience. Can is going to talk about creating interactive and generative audiovisual systems using Max, and also ways to integrate third-party applications such as game engines or P5JS to his Max projects. Okay, Can, the floor is yours.
Yeah, thank you very much, Umut. You are very kind. Let me share my presentation too. Hello, everyone. I was going to introduce myself, but Umut did it much better than me. So I can say I'm a new media artist. I graduated from Bilgi University Music Department. I've been working with Max almost 5 years right now. Yeah, that's it. That's the things about me, so I can talk about my works right now. I will show you a few of my works. Most of them are interactive, generative audiovisual installations, and most of them are made with Max, and there are some third-party applications that I use, and I will show them how did I do that very briefly. Let's watch this video. It's about one of my work. It explains how it's working, how was it in the exhibition space, and we can talk about it afterwards.
Good.
The main idea was to create a room that remembers the sounds that were produced inside it, so people can communicate with each other, detached from the time. Only being in the same space was enough for it. That was the main concept that I come in mind when I first started this project. I want to talk about how is my process to create this kind of projects, and finding my needs and creating tools according to that. In the first place, there was a basic concept, creating a room that remembers the sounds that were produced inside it. And some tools that I needed because of that. One of them is a tracking system to see where the people are in the room and map these sounds to these people, and also examine the motion in the room, so it can trigger the sounds to create this soundscape that is memories of the room. Sound recording, processing, and trigger systems, and visuals that represents the memory of the room. At first, it's a very basic tracking patch. It extracts the last image from the image before it, so it finds the difference comparison to each other, which is motion in the moment. For optimizing the image for analyzation, I use Jitter, which is brightness, contrast, and saturation adjustments on the image. RGB to Luma, which is it turns the image to black and white, so you need just motion, not the colors. And lastly, for finding the place that where the motion happens, I use fine bounds, Jitter fine bounds. But I will suggest you to use if I done this project again, I will switch this patch. Jitter.cv computer vision package that Jean-Marc wrote. There's a really good blob tracking packages there, and I will suggest you to use that. And there are some great tutorials in the internet for using that. I want to talk about the recording. If the amplitude of the sound passes a certain threshold, it starts to record and disables the trigger of any sound that will play for 10 seconds. In the end, it looks at the general loudness of the 10 seconds, and if it is loud enough, it records it into its buffer. That is the recording phase. For the analyzing, there's a really basic analyzing tool. It analyzes the peak to sustain ratio for recording, which determines how to treat the sound when deformating it. It's working very strict way. If it's a punchy, crippling sound, the grain size of the granulation gets smaller, and it's a tailed, sustained sound. It gets bigger. For triggering, it plays a recorded sound when someone passes the location recording. There is a window of every sound, and someone passes there. It starts the sound and stops the recording process. For sound processing, I'm using Petra package. It is working really great. It's a very good granular package. I will suggest you to use that. In this case, I'm manipulating grain size and pitch, and of course the mix of the dry signal and the wet signal when deformating the sound when the room starts to forget. About the visuals, 8 particle systems for 8 different memories. The sound buffer, sound capacity of the room is 8, because it can change room to room, by the way. If it's a bigger room, you can multiply it. But for this specific room that I exhibited this project, it was 8, so I used 8. there's 8 different particle systems. For the abstracted room, I used JIT-GL grid shape and JIT-GL mesh. But in a sketchy way, I export the vertices from grid shape to JIT-GL mesh. You can see it right here. Then played with some settings in JIT-GL mesh, polymode and stuff, and it generated a suitable image for me. But for my other project, I did differently, and I would suggest you to do learn some other 3D editors like Blender, especially if you are dealing with this kind of shapes and manipulating this kind of visuals. Definitely learn some other 3D objects, 3D editors, edit there, export it, use JIT-GL model and import it via JIT-GL model and work around that. In this transform feedback site, every particle system has 20,000 particles inside it. The important thing about doing the particle system with transform feedback was it is much more beneficial to use GPU-based system, especially doing this kind of visual works. If I used JIT-Gen or some other CPU processed workflow, I couldn't use 20,000 particles. Definitely 200 particles might be worked because I did this project on a very old MacBook Pro. It was 2012, and it hasn't got any dedicated GPUs and stuff. So if you are doing this kind of work, I will suggest you to learn shaders. Let's get into transform feedback shader. For transform feedback shader, in this when the OpenGL 3 package came to Max, it's a very good tool. In this shaders, you can define your JIT-GL buffers attributes and call them inside transform feedback shader, such as position of the vertices, colors, normals, and some other vertex attributes. In the loop of the code, there is a basic point attraction system. You are giving a target and a force. The particles follows that target. In my case, it is the sound amplitudes, the memories amplitudes. So you can see the brain's visualization. And for doing this kind of particle systems, I will suggest you to check it out. Federico Amazing Max tutorials. It's been very helpful to me. His YouTube videos, he has a very long series, and I will suggest you to check him out. Trace of memory is done. The hand, this is a later project. It's my latest exhibited project too. Let me explain the basic framework, basic concept of the work. The hand's concern is to create a bond between different people with the help of the intuitive nature of the gestures. The hand is an audiovisual interactive installation that evolves with every encounter. It records every gesture from its audience and uses it to enhance its communication skills. The only way to interact with the work is by your hand. It tracks one of your hand skeletons with a camera. By making gestures, you can interact with the sculpture of a hand. The piece records your gestures to its neural network and creates connection with past encounters. It will deform, reform, and move according to your gestures. At the core, it's an instrument that will connect you and who played it before. If your gesture matches with an old one, it will play the old one alongside yours. There's a video again. We can watch that. Then I can show you some patch screenshots. That's it. On the top of the video, there are the performing notes of the work because it's an instrument, and that is the way that I tell people how to play it. They read it and find a way to play with it. That was the experience. Let's get on. For the skeleton tracking, I use ML5 JS sketch that is using hand pose database. It tracks 21 joint of a hand, and I transfer these coordinates of the joints to Max via WebSocket. It's a JavaScript library and not for Max. If you are interested with doing not coding, you will be familiar with not for Max. And the ML5 library is written over P5.js, which is a processing foundation and processing the language processing's JavaScript package. I don't know. Yeah, let's get on. This is the node objects code. It opens a server over WebSocket and takes data from hand pose via WebSocket, and you can open this array with some other JS objects. Yes. Hand particles and room. The hand particles is the hand sculpture that you are seeing and you are deforming with your hand, and the past encounters are deforming. It is a very similar particle system to what I'm using at the traces of memory, especially ones that are following your hands. But the hand sculpture has a different few parameters, and it works a bit differently. It has a base shape, and if there is no disruption, it returns that. When I talked about Blender and using 3D editors on my on traces of memory, I was talking about this. You are editing this kind of visuals in objects in Blender, and you can import them into Max via GL model. Transform feedback shader has a few more parameters. One of them is the base shapes, base shape vertices. In traces of memory, when there isn't a disruption, the particles will float in the air. In this one, they will merge into the reference shape. I don't know what to tell. It's a particle simulation. On the sound side, there are 8 different granular devices I'm using actively. Again, it's Petra. 4 of them are mapped to your hand gestures. The other 4 are the ones that are learned before and triggered. I'm using convolutional reverb of Ableton. And I'm using compression of Max MSP. There are some libraries, I guess. I'm not sure which one, but I'm using built-in compressor of Max. And all there is sound design. All the rest of it sound design and manipulating these parameters. For the gesture recognition, I use the Move package from package. It records every gesture and compares to the incoming gesture. It works like that. It's working very good right now. In this case, as you can see, there are four different data income, X location of the hand, Y location of the hand, Z location of the hand, and the openness of palm and palm, closeness and openness of palm. Thank you for listening to me. That's it. I think we are right on the 19-minute mark. In the breakout room, I can also talk about some other projects I did. Thank you very much for listening to me. See you.
Thank you, Jen. It's a fantastic presentation. It's really great. It's awesome how you're mixing all of these different objects and concepts and all these external packages into really cool artwork.
Thank you very much.
So as John said, we don't have time for questions right now, but after all the presentations, there will be breakout rooms where you can talk further with all of these awesome artists. But next up is Josecarlos Florez, who is a Peruvian new media artist and an independent researcher currently living and working in Barcelona. His area of research focuses on the fusion of art and open source technologies. He works on projects involving creative coding, sound, robotics, light, generative visuals, data visualization, digital fabrication, Internet of Things, VR, AR, AI, pretty much everything, I have to say. And his work has been exhibited in Peru, Spain, and the United States, also in art festivals such as Sonar Plus D and Ars Electronica. He's going to talk about his work of FLOWRZ, which is a generative audiovisual composition created from mathematical algorithms which generates a post-digital landscape characterized by a high synchrony between sounds and visuals. What that exactly means, I will leave to Josecarlos to explain.
Hi, guys. Well, as Umut say, I'm Josecarlos. I'm Peruvian digital artist who work and live in Barcelona. I start my art adventure in the sculptor program. So after that, I came to Barcelona to make a master on digital arts. And then I knew the possibilities of programming and the hardware stuff. So I started doing my own experiments and getting deep in the rabbit hole. So right now I think I know a lot of small things of different knowledge. I don't know if it's okay. So at first I'm gonna show you. I'm gonna share my. I want to share my computer, my screen, but I think how can I do it? Okay, I got it. Okay, guys, can you see my?
Yep,
screen?
I can see it.
Yes.
Okay, perfect. Well, this is my webpage. This is the stuff that I do. I mix like physical objects with light, robotics, in digital fabrication to print my own cheap robots, or I do, for example, stuff for VR too. But in this case, I'm going to talk about how I use Max. This is the project that I'm going to show you. Maybe we can see first my first try, and then we can talk about this. Okay. Now I'm gonna explain how is my approach to this project. So I start working with Max, but at first with pure data. It was for control some lights, create some basic sounds. Um, I was doing like 8-bit sounds and make some visual with gem, very basic. So after that, I left to pure data and changed to VVV. Uh, on VVV, I started doing like generative stuff because I all the time love the work like the people like Ryoji Aikida. I don't know if I'm pronouncing his name good. So I started to go by programming with VVV and start to learn, I don't know, make lines, points, stuff like that, and then mix with the pure data and make like better basic sounds. All sounds like 8-bit stuff. And then I start to learn about the filters. The filters, I start to use filters for move for objects that move in DVB, and start to use filters in the sound. So then I discover a new more like organical movement and sound. Let me check. I'm gonna show you my patch. In this project, for example, I generate all the sound in Max, and then by OSC, I send all the data to uh, the graphical objects that I create in 4V. So in this time, I'm working like just by one side. The data move from Max to BBB. But in my future works, I want to do something like bi-directional. So for the sound, I use very basic elements. This one, for example, is like do you see the groove, kick, groove clap, groove snare? It's like the drums part. I make like a random stuff with that to play the drums on different sequence and mixing with different sounds. By the other side, I have like MIDI piano who play different notes. I put like some notes that I like chords, and they can make that they move in randomly between these chords on different times, on different with different parameters on the filter. And the other stuff is that I use the granular synth that I use this module that is like NW. All this one, I use the Gigaverb. Gigaverb it's a nice reverb that I got, I think, in this BIP module. I found this module. It's very friendly to make like synthesizers. You have different mixers, oscillators, filters, effects that are built, and you just, for example, change the parameters. But it's very fun and very easy to use, to learn. So I'm gonna put the sound of the pipe. For example, as you can see in the visual part, I've connected the granular this X and Y position for the granular synthesizers connect to the VVV lines that cross. So if you see they move, they are mapped like connected. I use a lot of random stuff. Basically, it's like a randomly, the random and the random and the random. On this way, I create a new version of this flower project. So I can show you the video. I think it's a next step. So as you can see, my goal, the thing that I'm looking for is to create like a very like mix, like graphical object and mix sound object and mix the parameters between them and create like a new audiovisual object with his own movements and sound. In this way, I do something. I make the sounds, and I left the parameters randomly, and I create the visual parts, I create the parameters, and the randomly control of the parameters of the sounds control the parameter of the visual. And in this way, I found a very high synchrony. Right now, I can show you how is another way that I'm working with.
Josecarlos, so we
tell
are
me.
slowly running out of time for your presentation.
Oh,
so
sorry.
we can wrap it up, but I already see questions popping up in the chat. So I think there are a lot of people who want to look further at your work after the presentations.
Okay, perfect. So my time is out.
Yeah, so you can just wrap it up if you want to.
Okay, so no, if you want, if anyone has a question, I can be in the rooms after the last presentation, and we can talk about that more relaxed.
Great. Thank you, Josecarlos.
Thank you very much.
Great work. It's really cool to see you using just random chance, really basic elements, and you make something so complicated and cool like this. I love that you mentioned Ryoji Ikeda, because I immediately thought of him when I saw your work. So
sorry for my bad English, but sometimes I think in Spanish, and my language, it's very slow in English. Thank you very much, guys.
Okay, all right. So as I've said, after the final presentation, which is coming up in a few seconds, you will be able to, of course, talk further with Josecarlos about his work. But next up, last but definitely not least, is Samuel Pearce-Davies, who is a friend of Music Hack Space. You might have been part of at least one of his workshops. And he is a postgraduate researcher and associate lecturer at the University of Plymouth, UK, and a member of the Interdisciplinary Center for Computer Music Research. With a background in classical music, it was his introduction to Max MSP that brought Sam into the world of computer music and algorithmic composition. In this presentation, Sam is going to talk about incorporating artificial intelligence systems in generating new sounds, images of sounds, and how it all ties together with Google Deep Dream. So if you're with us, Sam, the floor is yours.
Yeah, thank you very much, Umut. So yes, as Umut said, I'm Sam. I'm currently living in Cornwall, UK, and working and researching at the University of Plymouth. I'm just going to start sharing my screen as well. Let's see that all up. There we go. So my project, as it says here, is sonic blending with Markov chains and spectrograms. So I've been working with Max MSP since sort of early 2015. I was very much had very little knowledge about music programming or just programming in general beforehand, but I was immediately very taken with Max and with the possibilities that were there for sort of generating music, generating sounds through the algorithmic composition, generative music, and more recently getting into a little bit of light AI work and machine learning. So for my undergraduate project, I worked on a big complicated algorithmic composition system for generating entire pieces of very rudimentary EDM from scratch, just entirely in Max. And then since I've been working at Plymouth from my master's, my research master's into my current PhD, which I'm in the process of writing up. I've been working on, as I say, machine learning for generating sounds from scratch. And the initial inspiration for that came from, as mentioned, the system of Google Deep Dream. And as it says here, this is not a PowerPoint presentation because I'm doing it all in Max, because why not? We can achieve the same thing and more all in Max. So what is Google Deep Dream? Google Deep Dream, if I try and move everyone's faces down out of the way somewhere, you can still just about see it. So Google Deep Dream is an AI art program that almost came about by accident when a group of Google researchers were trying to get a better look into the inner workings of neural networks to understand how they learn what they learn about data. You know how when you do a Google image search for a particular tag, you'll get various millions of images come up, and the majority of those will all have been tagged and classified automatically by Google's neural network systems, which are designed to recognize features in images such as cats or dogs or mountains or trees or anything like that. And as I say, the idea behind Google Deep Dream was, can we take a look at how neural networks are actually learning to classify different features in images? And they essentially reverse engineered the process where they took a neural network that had been trained to recognize a particular feature, such as cats, and then get it to progressively change another existing image, which they started just with white noise, to make it better fit the neural network's understanding of what a cat image should look like. And through that, they were able to determine exactly what features the neural network was learning specified cat and any other feature that you can imagine. But the interesting thing about that is if you take, rather than just an image of white noise, if you take an existing image such as this landscape and progressively alter it to fit cat, then you get things that look slightly like this. And if you run it for a few more iterations, you'll get something that looks a bit like this. And for a few more, and you get something like this, which is obviously completely insane, but really interesting generative artificial intelligence art, essentially. It's kind of trippy backgrounds where you're seeing cats in the trees and the mountaintops and everything. And when I first discovered this, I was quite taken with the idea and thought, well, is there a way that we can achieve a similar thing, but for sound or for music? For instance, taking a particular instrument and progressively altering it to sound more like a different instrument, or some interesting combination, timbral combination of the two. So for that, I thought, well, let's start with, if we know that artificial intelligence systems react very well to images, why not use images of sound? And you may be familiar with spectrograms, which are essentially, to vastly oversimplify, are an image of a sound. And if I just load up quickly the default Max Anton sound file, which you may be familiar with. Anton, it's a classic. There is a way in this patch here, which I found, I was shared it by a member of the Max community. I think it was originally shared deep in the Max forums many years ago by Volker Brom, but this is essentially a way of generating spectrograms in Max using Jitter and various things like that. And generating here, this one on the left is an amplitude spectrogram, which is essentially mapping. If you imagine we have a series of sine waves from 20 hertz up to 20 kilohertz, all with particular amplitudes at frequencies over time, then with enough sine waves, you can essentially create any sound that it is possible to create. So you have the amplitude values for those sine waves here on the left, and then the phase values on the right. And if you have those, then you can resynthesize the image back into sound, essentially. And so you can hear with Anton, you can see the little warbling at the end. This is the tremolo in the high. At the end, you can see that visually represented there. And then to show a completely different file, we have Jongli, which is good old Max inbuilt drum loop. And you can see how visually distinct it is from the original one. And so at first I was thinking, great, I'll use this. I'll try and do something interesting in Max with Jitter to, try and blend these together and do something like that. But I ran into a slight hiccup where, and you may have already noticed here on the left where I've tagged the frequency values. We've got 20 hertz at the bottom, great. 20 kilohertz at the top, great. That's the ideal range, maximum range of human hearing. But in the center, we have 10 kilohertz, which obviously is halfway between. But as many of you probably know, frequency does not scale in a linear fashion. It scales logarithmically, where you go up an octave, you double the frequency. So the ideal actual center point of the frequency spectrum is probably closer to 1,500 hertz as opposed to 10,000. And just to demonstrate the issue with that here, I generated a sine wave at 660 hertz, which has a lovely waveform up there at the top. I'm just going to turn it down slightly, but you can see 660 hertz. And if we hear that, it's not exactly a low note, but on the spectrogram as it is visualized here, it is almost at the bottom. So the vast majority of the sound present in most sounds that we listen to or music files was condensed in the bottom sort of 10% of these spectrogram images. And due to my lack of experience of working with Jitter and manipulating the way that it was doing the Fourier fast transforms to generate the spectrogram files, I was unable to work out how to change that. So I kind of went to the dark side and used Python to generate some better looking and more usable spectrogram images. So if I load this up next, there is an alternate version of spectrograms called MEL spectrograms, which have a more accurate logarithmic scaling on the frequency axis there. So you can see right up here at the very top, there's 20 kilohertz, which it doesn't show, but we're already down to 8 kilohertz when we get just down to this small bit here. And just to give you an example, this is an acoustic bass sample. And that's what that, there we go, you get a little tap as he takes the finger off the string at the end there. And we've got a flute. And a mallet, so I think it's like a xylophone or something similar. And an organ. And all of these sounds were taken from the NSynth dataset. NSynth is a project that was created by Magenta, which I believe is an offshoot of Google, where they were doing research into, again, AI for sound generation. And as a part of that project, they've sort of amassed this data set of, I think it's nearly 300,000 instrumental samples that are all 4 seconds long across various different instrument groups. So strings, flutes, guitars, organs, various things like that. And so for my purposes, anybody who's worked with AI to any extent knows that the amount of data that you're working with is often rather crucial. So having such a gigantic database available was kind of ideal. And in the Python code, which I'll just very quickly show here, you're able to generate the MEL spectrogram, as it's called, but crucially take it and resynthesize it back into sound purely just using the amplitude spectrogram here. And without going into too much detail, essentially there's a process in Python that you can use which generates new phase values to match the amplitude spectrogram so that you get a sound that is more or less how the sound should be back. So just to give you an example of how that sounds, this is an acoustic guitar that was from the NSynth dataset. Okay, and then this is it after having been transformed into a spectrogram and then resynthesized back into sound. So you can hear a tiny little bit of artifacting in the background, but otherwise I think the sound quality is pretty good. So I started moving forward on the sort of thinking, right, well, I've got all of these sounds, I can do something with them to try and generate new sounds or new spectrogram images to then resynthesize back into new sounds, essentially. And that's where Markov chains come in. Now, if any of you have seen any of my my YouTube videos, you may be familiar with Markov chains already, but essentially they are a form of machine learning where you're basically looking at a spread of data, whatever that data is. It could be notes, it can be pixels, it could be anything you like, and essentially working out probability matrices for that data. So for any point in that data, you work out the probability of going to any other point in that data. And that can be a bit hard to conceptualize. So let's give a musical example. If we take Ode to Joy from the fourth movement of Beethoven's Ninth, you know, Freude, schöne Götter, Funken, etc. If we try and quickly construct a Markov chain for that melody, we have to basically look at what data points are present in this melody here. So we've got 5 notes in total. We've got C, D, E, F, and G. So in order to construct a Markov chain, we have a look at each of the notes, see how many times it occurs and what it is immediately followed by. So E occurs 5 times in this data set here, and it's first followed by another E, and then it's followed by an F, then it's followed by a D, and then it's followed by another E, and then finally followed by another D. So we take that and we map that to probabilities using an I table in Max, which is a very easy way of doing probabilities. So for instance, this is our probability matrix for E. So we say that E has a 0 probability of going to C and a 0 probability of going to G, and it's got a double chance of going to D or E than it has to go to F. And we'll see if we start clicking a bang into this I table. The I table works as like a probability table if you bang it like that, which is quite nice. So I'll keep clicking it and we'll see that we're getting D's, E's, and F's out, but nothing else. And on average, we'll be getting D and E twice as often as F. And then if we extrapolate that and do that for all 5 notes, so do the probability matrices for all 5 notes that are present in this melody, then if we start banging them all sequentially, then we can get out a melody which is certainly not the same as Ode to Joy, but definitely follows the same rules as Ode to Joy. And without letting that play forever, basically, that you will never see a note followed by another note that is not present in that training data. And that is essentially how Markov chains work. Markov chains are just building up a probability matrix for any data that is given to it. But doing that by hand is a little bit of a pain. So helpfully, there is a very good library by Benjamin Smith called ML.star, which includes the ML.Markov object, which does that all for you. So for instance, we've got ML.Markov here. We send it in some training data, which in this case is the tune from Twinkle Twinkle Little Star. You click build, which tells ML.Markov, work out the probability matrix, and then you turn it on. And again, that will sound something like Twinkle Twinkle Little Star without being exactly the same. And you can change the order of the Markov chain, which essentially says how many previous states it considers relevant when estimating the probability of another state. So for instance, if we change that to 2, it will consider not just the note that it just played, but also the note before that and how often a note was following those 2 notes one after the other. So the probability matrix then grows exponentially in complexity. But then you'll hear, if we do that, then every note is going to be double because that's how it was present in the training data. Every note plays twice. But more interestingly, we can feed MIDI files into the Markov chain as well. For instance, here, if we feed in the prelude from Bach's first cello suite, play it in really fast just so that it hears it all, and then click build, and then we'll hear this will sound something like. I'm kind of just speeding through this because I've covered this ad nauseum on my YouTube channel, which I will give you all a link to at the end. But finally, I took all of that, the ML.Markov work, and extrapolated it out into a big, as it says here, MIDI-trained Markov chain. And if I just quickly put in Eric Satie's Gymnopody #1, feed that in there, play it all to it so that it hears it all. And then when that's finished playing in, we click build. And then we let it generate new states, and it will sound something like. So something like the Gymnopody. And I'd done all of this work separately to my current PhD work, just because I found the Markov chains really interesting. And I thought, well, hang on, I've been able to generate new melodies and things like that using the Markov chains. Is there a way that I can apply this to the generation of sound through these spectrograms? So what I did essentially was took these NSynth files. For instance, here again, we've got that acoustic bass that you heard before. And although this is a picture, it is also a load of numbers, essentially. For instance, if you have a look in this text file here, you can see this is what that spectrogram actually looks like. It's just being represented as an image there, but it is just numbers, which I've scaled here between 0 and 255 just to reduce the complexity of the data. This is inverted on its y-axis just because of how Max reads in files. But you can see if we go down to the bottom, because there's a lot of empty space in that spectrogram, there's also a lot of zeros here. So you can tell that this is that spectrogram file there. And so I thought, well, these Markov chains work very well with sequential bits of data. So why not treat each row of a spectrogram image as a separate Markov chain? So each row here, so like this one, we've got 115, followed by 131, followed by 137. If we treat each of these rows as a Markov chain, and then, as I say here, feed in this data to a bank of 256 Markov chains, because we have 256 MEL frequency bins on the y-axis, and try training that and seeing what on earth it generates and see what sounds that we can get out of it. So essentially I did that. And this was one of the first tests that I got out after it having been trained purely on guitar notes from the NSynth dataset. So there's a lot of bits sort of coming in and everything like that. You can see a lot of the frequency bins are sort of restarting multiple times, but it is remarkably guitar-like for something that is essentially just a probability matrix generating new frequency bin values. It sounds rather good for a guitar. So I improved, sort of worked on that and tried to improve on it slightly by, for instance, once each frequency bin reaches 0, make sure that it doesn't restart, just because otherwise we don't have all of these bits coming back in over the top, and increase the amount of guitar notes that it was being trained on. Which is quite quiet, but it's, again, quite guitar-like. But then, of course, the most interesting part is if we then start training it not just on one instrument, but on multiple instruments. So after it was trained on guitar and organ, it generated a sound like this. And when I tried turning off the functionality where it always stayed at 0 once it had got to 0, I thought, well, what happens if I just let it keep generating stuff out into, in perpetuity? What's it going to create there? I'm not going to play the whole of this thing because it's about 1.5 minutes long. And I think one of the frequency bins got stuck on quite a high value around there, which I think is going to be quite unpleasant, but I'll just put on a little bit of it and you can hear what it was generating there. Which again is kind of cool. But I ran into a couple of issues where, for instance, I needed to be able to tell the Markov chains where to start from, because up until that point, they were only, the first values that they would generate would always be the first values that they heard, which would always be like just verbatim from the original audio files, which wasn't ideal for getting a variety of output from it. And also, due to the limitations in how ML.Markov worked, I was not able to save the transition matrices once they had been built. Every time I closed the patch, I had to retrain it, which sometimes took upwards of 10-15 minutes time, which just was not fun to keep doing over and over again. So I bit the bullet and built my own Markov chains from scratch, a separate patch for generating and saving the transition matrices, and another one for taking from those transition matrices and generating new states. I'll just quickly go out of presentation mode, and I will happily talk over how these work in a little bit more detail at the end, because I'm just aware that I'm starting to get a little bit short on time. But essentially, they will generate a new text file, which can then be resynthesized back into sound. And I'll give you a couple of examples here. One of the first ones I got was this. Which was, again, it sounded at least as good as the ones that I generated from the ML.Markov object. So I knew that what I built worked as well as it could. And so the best way to improve upon what I'd done was to only train it on the same pitch. So just on, say, MIDI pitch 48 of guitars or brass or flute or whatever. So I've got a few examples here just of where I trained it on both brass, flute and guitar, just on MIDI pitch 48, but with different starting points. So starting from a guitar, starting from brass, starting from flute, and that sounds a bit like this. So just up a tiny bit. So you can hear very similar timbre, but quite a different attack. And then the same again, but a different note, just so you can hear it is actually a different MIDI note. Which are kind of interesting. But finally, what I worked on, which I thought was the sort of the one of the best outputs of the project, was a combination of mallets, so like xylophone style instruments, and organ, which this one, starting from an acoustic mallet, sounded like this. And a different one starting from an electronic mallet. And because they all seemed to sort of cut off before they'd finished playing, I decided to do one that's twice as long. So now we've got sounds that are purely generated from Markov chains and for specific MIDI pitches. So all you have to do next is either to generate just an entire octave of them and then feed them into a sampler. And then suddenly, we can go to the races. We've got mallet acoustic here, which we can play. Or the electronic one. And the long ones. And of course, I can even play them through MIDI. And just for a bit of fun, I thought if I put in a MIDI file of the battle music from the first Pokemon game, that would sound a bit like this. Etc. So that is where my PhD project is up to at the moment. I've done some additional work in with some slightly different ways of generating sounds using non-negative matrix factorization, but that's a whole different story. But essentially what I've got lined up for the rest of this is to just generate more and different combinations of different instruments and try using not just individual instrumental sound files, but much longer multi-instrumental sound files and see what on earth the Markov chains can generate from that. And then essentially compose several pieces of music using these new resynthesized samples, and then get it all written up and nicely polished and presented, and then yeah, it should be away. So that is all I have for today. I hope that that's been interesting for everyone, and if you have any questions, then as I said, I'm sure we'll have plenty of time to go through them all and have a bit of a deeper look at the Markov stuff if necessary.
Thank you, Sam. Wow, it's really fascinating stuff. I can say as a composer, my mouth is watering just thinking of all the possibilities and things you can do with this. It's really cool. And I already, again, see some questions beginning to pop up. So maybe this is a nice lead-in for me to first finish the recording. So if you're watching this on YouTube in the future, thank you for watching.